presenting mode. But yeah, I am so excited to talk with you today. I really won't be focusing very much on my research, as my title suggests. I'm really going to try to highlight some of the findings from the recent AR6 IPCC assessment, and really do some deeper dives into the solution space, both those that are implicit in the first assessment report, as well as those that might help folks kind of tag on to the scaffold of solutions from wherever they may sit, including, I think, some amazing opportunities to engage as scientists in the climate solution space from wherever you may sit. So very excited to get going here, and I have so much to share, so I'm going to be mindful of time, and I'm really looking forward to that discussion. So as Gabe said, I really started this journey as a paleoclimate scientist, and thinking about how what it meant to try to track climate extremes in the geologic record, try to understand what trends were already emerging from historical records that run up to present. Those are the kinds of records that I work with by and large. And think about, of course, what they mean for our future. So reading rock records is my my old day job, if you will. And in that, I was very honored to work alongside Gabe in our mutual obsession with water isotopes. Right, water isotopologs. We should really be precise in our language here. So thanks to Gabe for joining that crusade, which is never ending. And really what my latest work is focused almost exclusively on climate solutions and transdisciplinary frameworks that work across sectors to put science into practice. So this is one of my favorite opening graphics from Ed Hawkins about the warming stripes, which just communicates so clearly where we've been and where we're going. And of course, it wouldn't be a paleoclimate anchored talk if we didn't include the full pages 2K illustration of these warming stripes, which go across the last 2,000 years. The best available information that we have covers this interval, and each one of these stripes is a year. Got a beautiful graphic, even more illustrative of the stakes of where we are today. So thanks to pages 2K, thanks to Ed Hawkins. Bringing us up to present, of course, we have a variety of different reconstructed historical temperature curves from the major climate research centers globally. And so these are all convergent, that we've had a very warm decade, we've had a very warm several last years, and you may be wondering where we are going this year. We are not likely to beat a new global temperature extreme in 2021. This is projected by Gavin Schmidt, of course, from using NASA GISS data in this case, but looking at that brown tick and the associated uncertainties of his projections, just using year-to-date temperatures where we're likely to fall in later this year as the year wraps. So personally happy that we won't be toggling on to maybe even the top 5 years, perhaps, with 2021 temperatures, a bit of a respite. Of course, we have a massive La Nina underway in the tropical Pacific, which is pulling those temperatures down. So I'll talk a little bit about the relationship between the El Nino Southern Oscillation as a climate cycle and global temperatures. But first, I wanted to just pull this out of the IPCC report in contextualizing some of the changes in extremes that are hard to unpack from a global mean temperature curve. So I'm seeing a bit of lag with my video again, which is super annoying. So I'm going to stop and start that and hope it might fix itself. Okay, still a bit laggy. Okay, well, hopefully that I'll catch up with myself at some point in this talk. So this is basically a graph illustrating the global mean temperature, which you just saw in black, and the evolution of some temperature extremes. The coldest temperatures tracked on the blue curve at the top there, land mean temperatures, and then annual hottest temperatures in purple. And I think this is just an important conversation to kind of peer through something like the global average temperature curve and help people connect to the extremes that are happening on the ground. In this case, on the ground, literally warming faster than in the ocean, and cold extremes warming faster than warm extremes. And so this is something that is good to keep in mind as we talk to the public and as we think about the impacts that are going to occur as these extremes change in shape. This is where some of the largest impacts occur from a climate perspective. Okay. Now I have my mouse. Okay, so let's go back to that relationship between the El Nino Southern Oscillation and global temperatures for a second, because that's the work that I do is anchored in the tropical Pacific in the study of the El Nino Southern Oscillation. So 2016 remains the warmest year on record, and it will not be superseded this year with 2021. And 2016 was probably one of the largest, maybe top 3 El Nino warm events of the record, of the instrumental record. And so this is a picture from NASA GISS just illustrating the peak warming that occurred during that El Nino event. You see warming from the central Pacific to the eastern Pacific. There is kind of that broad wedge swath where ocean temperatures can reach anywhere from 3 up to 5, 6, sometimes even 7 degrees Celsius warmer than average. And 2016 in the Central Pacific, where I work, is illustrated by that big blue circle in the middle. My home away from home, if you will, actually was a record-breaking warm extreme associated with the 2016 event. And so down the left, this time series is indicating some of the years that I've been fortunate enough to travel down to the equator. So all the field expeditions I've conducted in my career. And then the reds are indicating either minor or major El Nino events in the bigger bold-faced type there. So I had the honor of witnessing the 1998 El Nino event as a baby graduate student. I got completely hooked on this whole space. I just thought it was an amazing phenomenon that our planet undergoes every several years. And there's still so much we don't understand about this phenomenon for the students out there, worthy of a lifetime of pursuit. We still don't even understand, for example, if it's changing in response to climate change, something that has dramatic consequences for regional temperature and precipitation patterns around the world. Okay, but I somewhat digress from my talking points. So here I'm just showing you one of the photos that Gabe was alluding to, how we use corals to reconstruct El Ninos at the equatorial Pacific, at the central Pacific sites. I work on the Line Islands. It's an island chain, in the Northern Line Islands specifically, at sites called Christmas Island, Fanning Island, and Palmyra Island. It's kind of the geographic middle of the Pacific. And this is a picture of me extracting a coral core from a coral colony, in this case, a living colony that's been growing over the last 50 or so years, and pulling out this time capsule of calcium carbonate skeleton. And each 1 to 2 centimeters is a layer of skeleton that's accreted. And we can drill down this coral skeleton and analyze the powders for geochemical and isotopic signals, and use those to reconstruct ocean temperature extremes of the past. We compare the temperature extremes of the past to those of today, and in aggregate try to understand if this climate extreme is changing in response to rising global temperatures. And I'm not going to go into this fascinating line of work because, as I said, I'm really going to be focused on some of the emergent work from the new assessment report, as well as some on-the-ground solutions work that I'd like to lift up. But I would be remiss if I did not note that my student last year, Pamela Groth, published our latest, greatest assessment of all the data spanning the last centuries and millennia from these sites, compiled all together to note that the last 50 years of that long baseline of ENSO reconstruction does show a significantly stronger pattern of events than the preceding centuries. And so using that information, we did say that the last 50 years are stronger, and that of course they may be tied to anthropogenic climate change, something that was still somewhat inconclusive in other data sets from across the tropical Pacific. And so the assessment from the IPCC report still noting a high amount of uncertainty with respect to this conclusion. So we won't belabor that because we're talking about the things that the IPCC says are certain, but I wanted to illustrate the scientific approach that we have used to try to contribute to this question and give a little bit of insight into why I'm very interested in climate extremes and their impacts. So this is one reason, is because in 2014, we were working on a very healthy, very diverse reef at these research sites in the middle of nowhere. And by 2016, after 10 long months of record-breaking ocean temperatures that far exceeded the threshold for coral bleaching, we saw 85% of the coral reef die. And so, it happened from one expedition to the next across 3 months. And it was very striking. And some of these corals have recovered. Obviously, the reef will never be the same. There is a different composition of corals there. The size classes are all different. We're talking about a reef that would need decades to recover to the reef structure and composition function that it had in 2014. And as we know, it doesn't have decades to recover before it will face the next coral bleaching and mortality level ocean temperature extreme. So that's kind of where I've also approached the work and thinking about what is the role for climate science on a warming planet? What is my role as somebody who has achieved a certain level of seniority in the field and knows a thing or two? What is my role in the broader public sphere with respect to the public discourse around climate science, the policies that are shaped around climate science, et cetera. So I just wanted to pivot to the AR6 before diving into some of its core findings. So getting involved with the IPCC AR6 report was maybe one of the worst decisions I've ever made in my life, because I had no idea what I was getting into. Everybody I talked to said, I don't know if you should do it. It's just a lot of work. I mean, I don't know. I probably shouldn't have done it myself. And then somehow at the end of those conversations, I said, well, it sounds like something I'd really love to do. So, you know, you just can't listen to wisdom. But at any rate, it was a 3-year process. It involved 156 lead authors from around the world. I was one of those 156. We would meet every 2 weeks since 2018 until the report's release in August of this year. And so obviously the pandemic disrupted that as well. And so we really had to scramble and try to maintain the momentum that was dictated by the published date of that report, which was tied to certain international climate conferences. What are the core findings of the AR6 report? There are many, many, and I encourage you to go to the website and download the summary for policymakers, which I think it weighs in at 46 pages or so, which is the longest ever. It was very hard to make it so concise, if you would believe that, because there's a lot of information that it is really important to highlight about our changing climate and what it means for future decades, centuries, and our choices over the next several years. But here's some of my distillations from that report. Really important language around anthropogenic influence on warming, noting that it is now, quote, unequivocal. So that's an update on previous language and verbiage. And then I think there was some very, targeted use of paleoclimate information in this report that was brought in alongside the instrumental record through every chapter of the report. So paleoclimate scientists like me would sit down next to instrumental climate scientists and modelers from across the teams and write these chapters together. So for the first time, paleoclimate didn't have its own kind of dedicated section, but was integrated throughout. One of the results is that we were able to uplift some quantitative comparisons to our current climate and how it's changing with respect to the vast trove of paleoclimate information that we have as a community. So I love highlighting these points. They are backed up by amazing assessments in the report. Most notably, chapter 2 is where you will find the observational paleoclimate information. So the rate of warming unprecedented in the last 2,000 years, I don't think that surprises anybody. Current temperatures are likely unprecedented in at least 100,000 years, going back to the last interglacial period. And ocean pH levels at their current level of acidity are unprecedented in the last 2 million years or so. That last one, I think, is really something that we can say anew in this report. And it's quite striking and very humbling to think about just how far we have reshaped the fundamental chemistries of our planet to make this so. So I wanted to highlight that one in particular. Moving on to some of the findings around weather and climate extremes, which are one of the exclamation marks on this report and is subject of hundreds of news reports over the last month or so. And I think this is because, of course, we've seen the headlines raining down upon us from the kinds of impacts that are listed on this very list, right? And so, it's almost like climate scientists had a crystal ball. We've seen some of these things coming, but some of them are unfolding in real time in ways that have provided opportunities to help the public link the science of the IPCC assessment report to what people are experiencing on the ground, what they're seeing on their TV screens. So all of these are, some of them are brand new categories that are mentioned in the report quite strongly, backed by attribution science that's advanced significantly. Records, historical records, instrumental data that are much better than they were even 10 years ago. And last but not least, models that are helping us link the warming levels to the physics of climate and weather extremes in better ways. So our models are also getting more accurate. So those are some things that I would highlight that have strengthened in general these statements about climate and weather extremes and links to warming. Fire-prone weather called out in the report as an unequivocal increase in certain areas, including Western North America and the Mediterranean regions, where we've seen these headlines emerging about horrific wildfires. Agricultural and ecological drought on the rise globally, most notably in key regions like Western North America, the Mediterranean, portions of Africa, and Asia. Extreme rainfall and flooding on the rise as well, most notable where we have the best records of rainfall, because this is a tough one to see in the data. Eastern North America called out, Europe called out as well there for the extreme rainfall, in other words, relevant to the United States. Marine and land heat waves relevant globally. There's nowhere that has not experienced heat waves and heat extremes on the rise. And then last but not least, of relevance to our communities here in the Southeast, the trends towards larger percentage of tropical cyclones that are falling into categories 4 and 5, notably increasing over last decades. And this very important text that I quote from the IPCC report, because I don't want to mince words here, this trend is unlikely to be caused by natural variability, according to the IPCC report. And so that's a pretty strong set of attribution claims, the strongest to date. And some of these are brand new to this assessment. Last but not least, we have some findings around longer term commitments that are highlighted in this report, and sea level rise is certainly one of them. Ocean acidification is another, of course. These longer term memory pieces that involve the ocean, the atmosphere, and ocean and the ice sheets. Sea level rise, according to the IPCC, 1 to 3 feet by 2100, with a possible 5 feet of sea level rise if you include higher end warming levels combined with ice sheet instabilities. These are flagged as high emission storylines. So the idea is that there are paths we could walk and the natural system could walk that would land us in some of these higher impact categories. It's important for the public to be aware of what those futures could be that are science supported, but they're determined in a slightly different way than you would the standard assessments, if you will, that are reported in the IPCC. I'll show that plot in a minute so you see how that looks visually, and I encourage you to read the text. And then last but not least, this core finding, the 1.5 degrees C warming level, that ambitious target that was set in the Paris Climate Accord, not yet out of reach, but achieving it would require deep and sustained emissions reductions, and that enacted very quickly. So I'm just going to, just hook some of these findings to what we're seeing on the ground, especially here in the United States. Obviously, we're seeing year-on-year wildfires across the Western United States, record statistics coming out every year, whether it's percent burned, the number of fires, the number of communities impacted, the length of the fire season. It's just absolutely just becoming a year-on-year reality of kind of worsening trend, and one wonders whether this will keep accelerating as it is. Hopefully not, but this has become obviously a perennial feature of our lives. And this is some of the science I wanted to illustrate that is really helping to link ongoing anthropogenic climate change and warming to these fires, especially out west. This is a paper by Goss et al. In Environmental Research Letters last year. And this is autumn wildfires and the links to temperature, precipitation, and fire weather, which are those hotter, windier, drier days. So you can see the increase in temperature quite clearly over the last decades in the upper left. You see precipitation going down in the lower left, but not appreciably. It's just at the edge of significance. but really the amount of fire weather increasing dramatically, the proportion of fire weather strongly trending, and the area burned, of course, strongly trending over the last decade. So this is one of those studies that helps us understand the role of warming in driving wildfires out west. So this is something the IPCC has pulled together in the assessment to say there's an increase in fire-prone weather in the Western United States and the Mediterranean region, concurrent with drought. This is something I think it's worth talking about, and I would just lift this up as an amazing science communication tool in this era when people are wondering what the total cost of these events are, and to make the point that we're already footing the bill for climate change in our economy. So this is put out every year by NOAA. These are charts of billion-dollar weather and climate disasters. So you don't get to be an icon on this map unless you caused at least $1 billion worth of damage. You could cause much more, but then some of them are, and I'll show you in a second. But this is just a great infographic to illustrate just how pervasive these climate and weather extremes are, and just how different in type that they are. Some are wildfires, some are tornadoes, some are extreme rainfall. Of course, we have the hurricanes and flooding scattered throughout. So very interesting approach that NOAA has taken, 18 separate billion-dollar disasters so far this year. The year is not over. And this is a graph timeline of the weather and climate extremes through time. Again, this is just the billion-dollar disasters going back to 1980. And I think the trend here is unmistakable in nature. Big increases in severe storms, which are the green, but also big increases in flooding, which is the dark blue, and big increases in wildfires and droughts, which are the orangish colors. So very, very worrying is the right-hand axis. So the right-hand axis is actually cost in billions of dollars per year to our economy. And this axis is maybe hard to read, but it's in the hundreds of billions of dollars. It goes from 0 to $450 billion per year. You have to track the gray line on this plot. You'll see that 2017 topped the charts at a total cost about $440 billion to our economy, and that horrific year of course, unending hurricane hits that we took. And then you can see 2021 here, though, really ticking up into the high cost categories with Hurricane Ida, an estimated $60 billion of damages just from that one storm and its ensuing fallouts across our country. So those are some very large numbers. Those are the kinds of numbers that they debate in Congress right now. So it's worth reminding ourselves, as well as the general public, that this is already something that we can see in our economy every year. And some of these have just outsized hits, not just to our economy, of course, but to people's lives and livelihoods and intergenerational poverty that is baked into so many of these extremes. So, and some of these are very close to home here in the Southeast. These are storms that we all lived through. Hurricane Lane, of course, was in Hawaii, Hurricane Harvey and Hurricane Florence here in the Southeast. And all of these statistics here are statistics that are in and of themselves represent some kind of category of National Weather Service all-time record for those events. Really indicating the extreme rainfall is becoming not just wrapped up into the overall pattern of precipitation that we're experiencing, especially here on the East Coast, but of course also folding into how tropical cyclones are manifesting and providing these opportunities for compound threats from storm surge, extreme rainfall, and of course sea level rise going forward. So this is from the National Climate Assessment, just noting the prevalence of extreme rainfall along the southeastern United States. If you're interested in digging into that, I encourage you to do so. But the southeastern US is where we see some of these large increases in extreme rainfall in the data set, allowing for the attribution that the IPCC was able to make. the hurricane piece is emergent, very interesting science. This is by Kosin et al. And PNAS last year. This is, again, the proportion of major hurricanes through time, and the idea that this is linked to warmer ocean temperatures, illustrated anecdotally by the path of individual hurricanes and how they strengthen over warmer waters. But of course, still an area of very intense research to try to understand the totality of factors that may govern tropical cyclones in a warming world. But obviously the trend is something that the IPCC has said unlikely to be attributed to natural causes. Okay, I wanted to focus back to sea level rise for a second, because to my mind, that's kind of like the sleeper cell of climate change. Right? It is absolutely a train wreck that is coming at us. In some areas of the world, it's already here. And I would note that the place that I work at in the middle of the tropical Pacific is a low-lying atoll with a maximum elevation of 5 feet. So 1 foot of historic sea level rise that we have had over the 20th century has meant a reduction in the available water resources that they have as the saltwater table comes up, and increased incidence of flooding during any number of different extreme rainfall events that occur in that region. So this is already having an impact, but to going forward, we have to turn to the IPCC to understand what the potential future scenarios are, and to realize that they extend far beyond 2100. They extend for centuries, if not millennia to come. And I really can't say this to the public enough. And I know as geoscientists, we may get this, but it's really an important talking point to help people understand that the decisions we make today will have centuries and millennia of ramifications. That's pretty deep. So here's where we are, 3.3 millimeters per year or so of sea level rise based on historic data. This is from the NASA altimetry satellites. And this is a project that I'm working on the coast to try to help some vulnerable communities get in front of that sea level rise that's coming down the pike. This is a project called Smart Sea Level Sensors. And in this case, I think this is actually not the slide I wanted to use. Okay, I'm going to talk about that in a minute, because that's the wrong slide. We'll talk about that in a minute. First, let's talk about our emissions choices and what they mean for sea level rise, and then I'll talk about how we're going to fix some of this, but not all of it. So the emissions choices that are baked into the IPCC scenarios that are run are as follows. You have these high emission scenarios. That's the maroon curve on the upper part of the plot. And that is a high emission scenario where we continue to increase emissions over the 21st century, and only at the last couple decades get our act together and start decreasing emissions. Obviously, a huge amount of cumulative greenhouse gas emissions. And then we have intermediate scenarios that reflect varying levels of ambition and action. And then we have, I'm going to highlight the ones on the bottom, which are the blue curves, which are the aggressive mitigation scenarios. So you can see where the temperatures that we land, I've kind of put on the side here. So in the high emission scenario, 3.5 to 5.8 likely range, all the way down to the 1 to 1.8 degrees Celsius. And then the navy there, the second to most aggressive, 1.4 to 2.5 likely. So even the navy one may be likely to miss the 1.5 degrees C target, but the blue one is likely to meet the 1.5 degree C target, okay, all things being equal. And so just look at the differences in these scenarios, because we're going to look at what they mean for temperature trajectories and, most importantly, sea level rise. All of these cumulative emissions are actually translating into sea level rise rates and endpoints that are very, very different. And all of this will be baked in this century. And arguably, a lot of it will be baked in this fall at COP26, where countries will either rise to an ambition in line with 1.5 degrees Celsius. And then, of course, they have to enact that over the next decade. So this is a lot at stake. The most aggressive emissions trajectories in line with 1.5 degrees C would have us at net zero emissions by 2050. That's essentially the goal for keeping emissions, keeping that warming at that 1.5 degrees C level. And then you have to walk that path. You can't do that overnight in 2040. It doesn't work that way. You have to walk a steady and aggressive path. Early actions have the highest benefit because you obviously do not get that CO2 in the sky. Later actions have less benefit because you already have CO2 in the sky from delayed action. So I just said about where that leads us and with respect to temperature change, but I wanted to show you the trajectories because at the most aggressive trajectory, this is from the IPCC, that light blue curve, not only do we have a likelihood of staying at 1.5 degrees C, but we also reserve the right to cool thereafter. So you can see that scenario kind of dipping down at that point. And so that's really the only scenario where we see kind of cooling in the latter part of the 21st century. And I think that's important for the public to understand too, that there's some aspects that we can try to reverse later this century if we meet that target. And those are opportunities that will be slipping through our fingers if we do not do that. So I think that's an important point. Back to sea level rise, because this is the kind of the scary part, as I said before. These are to 2100, the sea level rise rates for various scenarios. So if you take the model output alone, and they don't account for all the ice sheet dynamics, unfortunately, they try very hard and they do a fairly good job according to the experts, but they do not include some storylines that the glaciologists think might be possible, including accelerated decay of the polar ice sheets. And so this is this is in meters, this is 0.5 to 1 meter by 2100, depending on the emission scenario. But it's this low likelihood, high warming storyline that the IPCC is dotted here that can lead to those kind of, plus 5 feet cumulative sea level rise by the end of this century that they want to flag and that they're trying to illustrate to the public is possible in a warming world. The scary part is that by 2300, the IPCC calls out in the summary for policymakers numbers like these. By 2300, of course, we'll see year-on-year sea level rise for centuries to come. They bracket this to say that plus 1.5 to 10 feet in the lowest emission scenario by 2300. In the higher emission scenarios, you're looking at 6 to 21 feet by 2300, but that they cannot rule out 45 feet. That's like, that is, to me, insane number to have in an IPCC assessment report. It just makes me squirm physically in my seat when I read it. It's something that I think, we don't want to, beat this over the head of the public because it's a long way off. But what I do think it illustrates is just how much difference it makes these scenarios that we're talking about now and what's going to happen to 2050 actually will matter for centuries to come, and it will matter an awful lot. And so I think that's an important point to make to ourselves, remind ourselves, and when we talk to the public, to make that point, because this is a really critical one. Okay, solutions, I promise, because we are out of time, both in this seminar and okay, that was very bad, and globally with climate change. So let's not lose any more time. We do need to kind of think about what it means to go all in on climate solutions. And, I wrote that op-ed in the New York Times that Gabe was talking about, because I think there are certain tools we might like to leave on the shelf. Solar geoengineering being maybe one of the only ones we might want to leave on the shelf. But otherwise, you really have to kind of take a holistic approach from nature-based solutions to adaptation to low-cost energy technologies, and think about different scales when we do so. Not just those controls at the global scale that people at COP26 are responsible for, but all the way down to our institutional levels, and our individual levels. It really has to be an all-in scale and a horizontal approach as well. So I'm going to briefly just talk about what I mean by that multi-scale engagement, because I think there's feedback loops that get triggered, which are actually quite powerful when we think about climate action on a scaffold like that. And there are scalar kind of trickle up and downs, in other words, that are levers for positive momentum that I have felt myself and I'd like to share with you today. So I woke up on January 1st, 2017, grasping at straws, quite frankly, and trying to figure out a way forward after witnessing 85% of the coral reef that I've studied for 20 years die, and the election of administration, which was openly hostile to climate science and climate scientists, and unsure what the next years would bring. So I started just committing to bike to work twice a week and walk my kids to school twice a week. And within about 3 weeks, I was biking to work every day. And, you know, it's just been a gift. And now I have 6 bikes in my front hall. I just got an e-bike. I'm like an e-bike stand account now on Insta. But at any rate, it has been an amazing gift to think about how this has unlocked potential in my own life. Not because of the carbon. I started it for the carbon. It's a carbon pittance. It's like 1,000 pounds a year of me biking around on my bike. But actually thinking about what it did as a ripple effect, it caused me to hold my first elected position as traffic chair for my neighborhood board. And I'm an elected official. And it also kind of spurred me forward in thinking about how I could engage at Georgia Tech for better bike ped infrastructure and down in City Hall all the time and signing all kinds of petitions and showing up at hearings. And that really illustrated to me the really hardwired ties between what I thought was an individual choice and some of the momentum that we need to build to make it an opportunity for more people to access that mode of transportation if they would like, that low carbon, co-benefit full mode of transportation. I love my bike. The other thing I did was I decided to try to go solar for my house. So we did purchase an array 2 years ago, and I can't shut up about it. And since then, at least 10 of my very close friends here in Atlanta, stone's throw away from my house, have also gone solar. And obviously, you know, thinking about advocating for favorable solar policies when they come up at the public commission. And then the one thing I do, which is flying less, I've actually committed to stay on the ground for now. And I did that before COVID in 2019. And kind of the structural tweaks and pushes and shoves that are engendered in that choice are something that hit the structural nerves of organizations and definitely strike a nerve across society in a vigorous discussion about climate justice, climate equity, and what we might be able to do in 2050 to move this needle. And then last but not least, everybody likes planting trees. I love planting trees, but obviously a lot of trees are burning down right now. So trying to keep up with our urban, our carbon sinks in general are probably losing battle. But this is auction area for urban resilience, urban temperature resilience, which I'll talk about in a minute, urban flood resilience, and of course, increasing biodiversity. So one thing at the organizational level, which I'm proud to share, something called the Carbon Reduction Challenge, which is a program that we run every summer. And we combine small teams of undergraduates with organizations, big and small. And we ask them to design and implement a large-scale energy efficiency project over the course of 10 short weeks. And so over time, they've identified these amazing pieces of low-hanging fruit. They build a business case for them because typically they're saving money. And basically, they've gotten their project implemented, I would say, about 30% of the time in the course of the summer. And so on aggregate, year on year, we've gotten better at this. And now each cohort that we're working with is avoiding the emissions of tens of millions of pounds of carbon dioxide. Now, I know carbon literacy is an issue. We know what $10 million are. We don't know what 10 million pounds of CO2 are. It's basically equivalent to running 30 homes fully solar for over 20 years. So that is a lot of CO2. And that is a scale that matters. And we're talking about cohorts of 20 to 30 students per cohort. So this again illustrates the power of individuals and moving organizational levers. And this is something that we could all think about accessing, whether it's through our universities, which are our closest organizational affiliation, but also through our children's school or our church or our mosque or anything else that we might do. How does this work out? This is the winning project from the last year. We worked with the ACLU to make a formal policy for work from home, as well as tweaking their HVAC and lighting settings to better reflect office usage patterns. And they just reaped all these carbon dioxide savings and delivered savings to the organization as well. So a great bunch of students, and the students are extremely passionate about this. They need these skill sets to navigate the 21st century. And the organizations love the branding opportunity. So this is a big win-win-win space, and I'm happy to share that information with anybody who's interested. Stepping up beyond our organizational level, we have a project here in Georgia called Drawdown Georgia. It's about 2 years old, and it represents a research-based map to achieve carbon neutrality in Georgia by 2030. So that is a very ambitious goal coming from where we are in Georgia, but we've outlined these 5 different knobs that we can reach for and exactly what it would take to get there. One of the exciting things that this project has done is identify the economic opportunities along the way and the equity wins along the way that can be achieved by pursuing some of these solutions. So I'm proud to be part of this. It was a consortium of 5 academic institutions come together for this with 30 researchers. So this is something that I'm also happy to share if folks are interested in how academics can come together across different departments and institutions to try to pave a way forward and show people that it's not the environment or climate change and the economy. It's not equity or the economy. You can actually have a nexus where you can achieve all of these things in the same breath if you have some evidence-based pathways to follow. These are some of our solutions. I'm not going to go into those in any detail. We have a top 20 list that we published and tried to advance with policymakers at many scales. Some of these are individual choices that can be helped by public policy infrastructure as well. So I want to note that. Okay, so the last thing I want to talk about is how we can use science to further resilience and adaptation on the ground, because obviously we are totally remiss in harnessing the power of climate science to keep communities safe today, let alone trying to get in front of the coming climate impacts over the next 20 years of certainty in warming levels and certainty in increasing climate impacts. Remember that list I showed from the IPCC report? All of that accelerates and scales with warming levels. The soonest we can turn this around is 2050. So we know we have a runway here that is increasing climate impacts. We have an opportunity to harness this information to keep communities safe. That is a lot harder than it sounds, but we can get going, and we as scientists have a role to play. Just to remind you what the IPCC says, I love this graphic. I think it just speaks to me, and I think it speaks to the public in really important ways. Talking about a 10-year heat extreme on land, starting with the pre-industrial period, those kinds of things at various levels may have happened once every 10 years. The present at 1 degree C of warming, they're happening 2.5 times more frequently. 1.5 degrees C in the middle bar, they're happening 4 times more frequently, that 10-year event. And then of course it goes up to a staggering 9.4 times in a 4 degrees C world. So when the public thinks, well, what's 1 or 2 or 3 degrees C, it's helpful to bring it back to charts like this that help them understand how much suffering has increased already and how much suffering will increase going forward. Now, of course, we have the fact that urban heat islands are disproportionately affecting low-income communities and communities of color, which kind of distills some of the climate justice issues in climate resilience and adaptation. This is an amazing map published in the New York Times last year, I guess, based on work by Jeremy Hoffman in Richmond, Virginia, that overlaid very detailed maps of urban heating and urban extreme temperatures with historic redlining in Richmond, Virginia, a practice that basically allowed for decades-long disinvestment in communities of color, predominantly African-American communities across the United States. This was a policy level decision, believe it or not. And so many of these communities are still grappling with the legacy of systemic racism as it has unfolded over decades. And part of that legacy is a landscape that is devoid of trees, very concrete and blacktop heavy. And in general, some of the hottest areas of Richmond, Virginia are these redlined areas. And so this is just to illustrate the issue of climate justice and how to get in front of these impacts in communities does mean focusing on the underserved, most generally speaking. And that's a challenge. I'm proud to be working on a project called Urban Heat ATL, which is depicted here, where we are putting these mobile sensors, these smartphone enabled sensors in the hands of students, 80 students from Spelman College, as well as Georgia Tech. And they're helping us get these incredibly detailed maps that you can see on the lower right So a standard NASA satellite resolution will give you a pretty good idea block by block, but we're talking about getting down into a meter by meter scale with these temperature maps. And we have over 1 million data points right now, aggregated across the 6 months that the project has been in existence. Proud to partner with the city of Atlanta as we think about what it means to be proactive to the coming urban temperature extremes instead of reactive, which is mostly where we land right now in Atlanta and many other urban areas. I point you to our website, urbanheatatl.org, to listen to this amazing webinar, 30 minutes of your life well spent, better spent than here probably with me, listening to this space from experts who are charging forward and trying to understand the science of solutions for these compound related problems. The second example I'd like to show is one that involves sea level rise on the Georgia coast, and then I'll wrap it up, where we have a pattern of very increasing flooding over the last decades or so, is depicted here by the tide gauge at Fort Pulaski, the only tide gauge, only NOAA tide gauge in Georgia. Some of these are, of course, named storms like Hurricane Matthew, Hurricane Irma, in 2015 and 16, but some of them are sunny day flooding that occurs from king tides or wind events as sea level rise begins to take an increasing toll on these low-lying communities. This is a project that I co-lead with colleagues here at Georgia Tech and community partners down on the coast called Smart Sea Level Sensors. You can check out our website, sealevelsensors.org. And it really is at the nexus of thinking about short-term and long-term solutions to what is already a flood problem down on the coast. And so we have these cool sensors. I think you can see the common thread here is the Georgia Tech idea of how can we put technology to work in context of climate science and solutions. And this has been great to watch the sensor develop in the School of Computer Science here. And this is an ultrasonic sensor. You can see the map of 50 sensors that we have, providing real-time data to decision makers and emergency responders and managers, as well as feeding into flood forecasting models that will help communities react to 3-day forecasts that are forecasting king tides, for example, forecasting storm surge, forecasting all kinds of wind events that are threatening communities. And this is great because they're very low cost. These are $500 in parts that can be assembled. They're powered by batteries or solar, and they use a communications infrastructure that doesn't have you paying for cell service because it uses the Internet of Things protocols. And these are usually assembled by high school students in the area. We are partnering with high schools to have these assembled. It's very possible they get these valuable engineering skills, and they actually feel part of the solution that they know will be lasting for decades. So win-win-win again. These talk to gateway devices. I don't want to belabor this point. These are a little bit more pricey, but they cover 1 to 4 miles of area. We've laid down a backbone of 14 of these gateways, and these can provide a great Internet of Things platforms for the city or any application that they want, right? So that's a really cool thing. 14 sensors times to gateways times $2,000. That is a really great community-owned infrastructure that we have supported. Okay, that's the wrong slide. Here we are. We're going to wrap up with this one. I'm just reminding you that the choices that we're going to make over the next 10 or 20 years will determine the rates and magnitudes of climate change on this planet for millennia to come. So, this is an amazing period to be a scientist, in my opinion. And it's an amazing opportunity to think about what it means to be part of the solution across different scales and leveraging your skills to plug into this scaffold that will have to be broad and deep across the landscape of science and technology and social science to really enact lasting solutions beginning today. So I'm going to wrap it up there. Thank you so much for this opportunity.